Good evening, everyone. My name is Aditya Sharma, and this is Power Plant System Engineering course being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program. And this is ninth week of this course, and pertaining to this week's content, we are conducting this session. Instructor for the course is Professor Niranjan Sahu, and I am a teaching assistant for this course. I am a research scholar here at the Department of Mechanical Engineering, IIT Guwahati only. So we shall wait for around 5 minutes before we start our session. So let's start after 5 minutes. Thank you. Okay, so let's start with the session. We can start with the session. So the Theme of this week's content is gas turbines and combined power systems. So individually, when we use gas turbines and when we use gas turbines in combined power systems. So this has been discussed uh, in this week's content. Also, gas turbines are extensively used in your aerospace sector that you all must be familiar with, right? So there are four lectures in this week's content, and we will one by one see these lectures and questions, some questions based on these lectures. All right. So also recently the private sector is also opening in aerospace sector. So a lot of startups are coming up. So you must have heard of one such startup, Agnikul, I believe, right? So there are other startups also. One is Skyroot, right? So okay, so we will start with our session. So first lecture is on fundamentals of gas turbines systems. So it has topics gas turbine cycles, then advantages, disadvantages, Brayton cycle, thermodynamic analysis. Okay. So the thermodynamic cycle that takes place in a gas turbine system basically is known as Brayton cycle. Okay. All right. Now, so first is your gas turbine cycle. So in this topic, what we have gone through, what is a gas generator? Okay. So maybe I can just so in a gas turbine, what we have an inlet, compressor, combustion chamber. Okay. Then is your turbine. Then is your NZL. I'm writing nozzle as NZL. Okay. Nozzle. Combustion chamber. So this is your common gas turbine cycle. Okay. The components that are used. So we have inlet from where we get our air. Then this air goes to your compressor that compresses the air. Then this air goes to your combustion chamber where we have fuel. So this air helps in the combustion of this fuel. Okay. Then we have a turbine where the products of your uh, combusted fuel. they expand, and then nozzle is used to further expand the combustion products, right? Then we have been told what is a gas generator. So gas generator basically is your compressor, combustion chamber, and your turbine. This is your gas generator, right? Then different types of cycles have been discussed, like direct open cycle, right? Indirect open cycle, indirect open cycle. Then is direct closed. Then is indirect closed. So what are these different types of cycles? So direct is when your working fluid is not being heated by means of a heat exchanger, right? So we will have a compressor here, right? Then we will have a combustion chamber here. Then we have a turbine here. Okay, this is your direct. Now what is indirect? We will have a compressor here. Okay. Then we will have what? Heat exchanger. We will have a heat exchanger. Something like this. Okay. So your heat will come from this. Heat will come from here. Okay. Right. Then this. Should I? Sorry. Something like this. Okay. Then here is your turbine. Right. This is your inlet. This is your exhaust. Like this. So heat is coming from this source. Okay. So this is your indirect. Here it was directly through your combustion chamber or some by some other means, right? So it has some other working fluid. This system has some other working fluid, and our turbine, right? This has some other this compressor and this heat exchanger and turbine system. This has other working fluid. Okay. So this is your indirect cycle. Then what is open? Open is when you have, so from above diagram we can see, so if you have some inlet here, then your exhaust is into atmosphere. Okay, so the working fluid is not going in a cycle, it's not remaining in the same working fluid is not remaining in the cycle. So if we have used the working fluid in a cycle, it won't be used in the next cycle, right? But if we close this cycle, right, if the working fluid that we have used that has entered the compressor and then exited the that has been exhausted from the turbine, that is somehow again used in your compressor, right? So this is your closed closed cycle. I hope this is clear, right? So in that context, only these different cycles have been discussed, right? Then is your Brayton cycle. So through diagram, you will see. So this is your PV diagram. Okay. This. This is a constant entropy process. Okay. These two processes. Let me draw the TS diagram also. So this is your this is your TS diagram for your Brayton cycle, right? Here we have two constant pressure processes. So I have just drawn the PV diagram and TS diagram for your Brayton cycle, right? Then, so your 2 to 3 is where you add your heat, right? So that means combustion chamber. Okay. 3 to 4 is where this is expanding, right? So this is turbine. 1 to 2 is your what? Compressor, right? And in 4 to 1 you will have your heat rejected, right? So these are your this is your Brayton cycle. If you have some doubt, you can answer. Sorry, you can ask. Okay. So a Brayton cycle has two isentropic processes and then two constant pressure processes. Okay. Then what is the next topic? Okay. Next is your thermodynamic analysis in this lecture number 21. Right? So in your thermodynamic analysis, different expressions have been given to you. One important is your pressure ratio, right? So if you see the above diagram, from there to this is P3 by P4. So at the inlet of your turbine, you have some pressure P3, and at the exit after expansion, you have some pressure, right? P4. So the ratio of these two is your pressure ratio, right? Then expression for turbine work is there. Right, which eventually if you see your lectures, it will boil down to this, which essentially means that it is somehow related to your pressure ratio. Okay, gamma minus 1 by gamma, you can denote it by K also, right? Then the same way your compressor work, right? The work that you do on your compressor. So this also, if you see your lectures, it boils down to this, right? Then is your network, which is, so what happens is you have expanded your gaseous products from your combustion chamber in your turbine, right? Then this turbine is also used to drive your compressor, right? And also used to generate, you can generate power also, right? Electric power, or it can be used in combined power systems also, right? So in these two ways, we have seen that it can be used in this week's lecture. But then what is the network in the whole gas turbine system? This is the turbine work that you have gained from expansion of gaseous products, sorry, minus the um work that is there in your uh, used in your compressor. Okay, so the expression for this is this in terms of your pressure ratio. Okay, this. So this is your network, right? Then if you see the thermal efficiency, we can derive all these, right? Not a big deal. So this is this, right? So this is about your different expressions, right? For your turbine work, pressure ratio, what is pressure ratio for your compressor work, and then net work, and then thermal efficiency. Then one important discussion is on effect of your pressure ratio. Yes. So this all this has been discussed in your thermodynamic analysis. Okay. So effect of pressure ratio on your specific work and your thermal efficiency. All right. So by means of graph, we'll see. So here we have our specific work. Okay. Here we have pressure ratio. Here we have efficiency. Right. So the scales for here and for here are different. Right. I hope you understand this. So what happens is, so the graph goes something like this for your specific work, and for your efficiency it goes like this. Okay. So this is for your specific work, and this is for your efficiency. Clearly you can see that for your pressure ratio there is some pressure beyond pressure ratio beyond which if you move, in that case the specific work will start decreasing or reducing. Okay. So in that case this point becomes your optimum pressure ratio, right? So this becomes your optimum. So this becomes your optimum pressure ratio, right? But if you see your efficiency, thermal efficiency, so with the increase in pressure ratio, this keeps on increasing. This keeps on increasing. So if you see this here, right, you can see that if the R with subscript P, if it increases, it keeps on increasing, then this term, what will happen to this term? This term will keep on shrinking, right? Its value will keep on decreasing, and uh, what will be the effect of that? Eventually your thermal efficiency will. All right. So this was about your lecture 21, fundamentals of gas turbines. Okay, so let's see now questions. So this here asks that your gas generator in a gas turbine cycle consists of which of the following? Question number one. So what is a gas generator? You have seen. Please try to think about it. The four options have been given. So if you see here four options: diffuser, compressor, combustion chamber, and turbine. So these four components devices have been used to create the options. And the gas generator we have seen. So what is gas generator? Gas generator basically is your compressor, right? Compressor, then combustion chamber, then your turbine. So if you see the options, B option is the correct option. All right. So gas generator, what is a gas generator? Then second is in a direct open type gas turbine cycle. So heat exchanger is used to transfer heat to the working fluid. A full stop should have been here. Okay. So direct and open. So we have seen here in our discussion that in your direct type of cycle, heat exchanger is not used. Okay. So this is your direct and this is your indirect. Yes. So here we are using this heat exchanger, right? Working fluid is not being heated directly but indirectly through some other system, heating system. So in that case, this is false, right? So because this is true for heat exchanger is for indirect cycle, right? This was your question number 2. Then moving on to question number 3. This again is a true or false type of question. So this here says that in a Brayton cycle for same temperature limits, so in a Brayton cycle for same temperature limits with increase in pressure ratio increases the specific work. So whether this is true or not. So by means of graph, you need to answer this question. Okay. So this is the graph. For specific work versus pressure ratio. So with increase in pressure ratio increases specific work. This is what the question says. So we clearly know that there is something called optimum pressure ratio, right? Related to this optimum pressure, there is a maximum specific work that we that the cycle attains. And if you will increase or decrease the pressure ratio from this optimum pressure ratio, your specific work will decrease. Right? So this, in that case, becomes a false statement, right? So this was your question number 3. Okay then. Next question is question number 4. In a Brayton cycle, which of the following is true about its thermal efficiency? So now the question is on thermal efficiency. 4 options have been given to us. So if you see the expression for thermal efficiency, from there you can answer this question. So what is the expression for your thermal efficiency? Please check this and then try to figure out. Sorry. The first option is the efficiency increases with increasing maximum cycle temperature. What is maximum cycle temperature, by the way? Right? And second option is increases with decreasing minimum cycle temperature. Then is increases asymptotically with increasing pressure ratio. Increases linearly with increasing pressure ratio. So what is the maximum temperature in the Brayton cycle? If you see this cycle, the temperature here, if you see at point 3, at point 1, if you see, is the minimum temperature, right? The at the entry of your turbine, the temperature that we have, and at the entry of your compressor, the temperature we have of the working fluid. That is your maximum and minimum temperatures in a Brayton cycle respectively. Then, so whether your thermal efficiency is dependent on these temperatures, one of these temperatures, or it increases, or it is a function of pressure ratio. So again, going to the graph, efficiency, thermal efficiency versus pressure ratio graph. This, if you see, so with your pressure ratio increasing, your thermal efficiency keeps on increasing. Okay, and the nature of this increase is asymptotic, right? The fourth option says that it is linear. But the correct option is C option. Okay, so after this, this was your question number 4. After this, we have question number 5. So this is a numerical type of question. So here it says that in a three-stage compressor intercooling in a gas turbine, power plant, the air enters the compressor at P1. Okay, and the discharge pressure is P4. That is, it exits the compressor, the whole three-stage compressor at P4. The intermediate pressures are P2, P3, where P3 is greater than P2, and P4. Sorry, P2 and P3 are the intermediate pressures, and the extreme pressures are P1 and P4. So the total pressure ratio of the compressor is 8, which means P4 by P1 is 8. The pressure ratios for all are equal. Okay, that means P2 by P1 equals to P3 by P2 equals to P4 by P3. P1 has been given as 81 kilopascal. We need to find out P3. Simple question. So how do we do that? This question. How do we do this question? Is it P2 by P1 equals to P3 by P2 equals to P4 by P3. Now also we know that P2 by P1 into P3 by P2 into P4 by P3 equals to P4 by P1, right? What we can do here, we can write all these as P2 by P1 because these are equal. That has been given P4 by P1. So this becomes P2 by P1 cube equals to 8. Implies P2 by P1 equals to 8 raised to power 1 by 3 equals to 2. Right? So this is a P2 by P1. Then we need to find P3. So what we can do is, so P2 by P1 into P3 by P2 is what? P3 by P1. We have this, right? Now P2 by P1, we can again substitute it with P2 by P1. P3 by P1. So this becomes P2 by P1 square. Right? P2 by P1 is 2. So 2 square equals to P3 by P1 implies P3 equals to 4 into P1. P1 is 81, 8 for the 32, 4 1 the 4, 34 kilopascal. So this is your P3. I hope this is clear. Right? So we can this way find out P4 also, right? Or P2 also if we want to find out. So this was question number 5. Answer. Right. Then is your next question. The next question is a bit lengthy question. This is a numerical type of question again. So first you see this information and then we will solve this question. So what the question says here. So four questions are there based on this paragraph. So we have a gas turbine plant which consists of two-stage compressor with intercooling. The intercooling is there. Then single-stage turbine is using a regenerator. Air enters compressor at here. Maximum cycle temperature is this. Pressure ratio is this. Effectiveness of regenerator is this. Airflow through the plant, rate of airflow is this. Then calorific value of the fuel is this. And its combustion efficiency is 0.93. Then isentropic efficiencies have been given of your compressor and turbine. Then mechanical and generator efficiencies are given as here. These two, 92% and 91% respectively. Then specific heats have been given for different gamma values. Okay. Then questions have been asked. The first is estimate the air fuel ratio. So for air fuel ratio, first we need to find out a couple of things because we will do it through energy balance, and in your energy balance you'll need to find out your few temperatures. Okay. So first of all, we will find out the temperatures. After that we will do all the questions. So what temperatures we need to find out? So first of all, let's see. Question 6 to 9 given, or maybe just I'll plainly draw the situation. Okay. Now to solve this question, question number 6, we need T6 and T7, right? And there are other questions also where T3 is also required, T4 is required, T6 is required, and T7 is required. Okay. T6, T5 is also required. Right. And then T2 and T1, these are also required. So first we will see if we have these temperatures with us one by one. Okay. So let's start from the beginning. So first of all, pressures have been given to us. Pressure ratio has been given to us. RP is given as P2 by P1, right? Which is 5. And P1 is given as 1 bar. So P2 becomes 5 into P1, that is 5 bar. This is 1. Sorry. Then your EI is given as. So why we are calculating these pressures? Because we will find out temperatures from here using our isentropic relations. Okay. So this is this. Then P1 is 1, this is 5. So if you calculate this, this will come out to be 2.23 bar. Then what we do now? Now from here we can find out T2. Okay. But to find out T2 we need TS also, because if you see NC is for compressor, right? Compressor efficiency is 2S this. I'll just write this down. Jot this down, this. Okay. Here what we have this, we have this, we have this. Okay. But this we don't have, this also we don't have. So first we'll calculate 2 subscript T subscript 2S, then T subscript 2. Okay. So how do we do this? So we'll use the isentropic expression or relation, sorry. So this we will use. Okay. Then because 1 to 2S is isentropic, right? We can use isentropic relation here. Then this we know is PI is 2.23 and P1 is 1 and this is 0.4 divided by 1.4. So if you calculate this, this will come out to be 1.25. Okay. Then what we do now? So this T2S we calculate T1. Now what is T1? T1 is given to us as 17 degrees Celsius, right? So T1 is 273 plus 17 equals to 290 Kelvin. So if you solve this, this will come out to be 362.5 Kelvin, right? Now Now using your this, so T2 equals to T1 plus efficiency minus T1. Here, this T1 is 290. This is 0.79. T2s we have used from here. And then if you calculate this, what will this come out to be? T2 is this. So we have now T2. Now what we calculate? Now we calculate the same way T4. We know T1 equals to T3. Okay, this you remember. From here you can see this. 1 to 3 if you see. Then we know again we need to find out T4s. So you know NC equals to T4s minus T3 divided by T4 minus T3 implies T4 equals to T3 plus T4s minus T3 divided by NC. Now we know T3, NC we know, but T4s we don't know. So we'll calculate it how? Again using isentropic expression. This way. Right? So T4s is T3 is 290, T2 is 5, and this is PI. 2.23 PI is 2.23 raised to power 0.4 divided by 1.4. Okay, because this is for air. Then if you calculate this, this will come out to be 365.24 Kelvin, right? So now we have this. So T4 equals to T3. T3 is 290 plus 365.24 minus 290 divided by 0.82. So this will come out to be 381.75 Kelvin. Right. Then for turbine, we need to find out. So T7 we need to find out, right? So we know NT equals to T6 minus T7 by T6 minus T7s. So T6 we know, but T7s we don't know. This we know, this also we know. So, but first of all, I'll write expression for T7. T7 is equal to T6 minus NT T6 minus T7s, right? So now to find out T7s, what we will use? Isentropic relation again. So T6 I am writing directly based on what? So here, because combustion products we are dealing with, so its gamma has been given, and T6 basically is, if you see, 875 degrees Celsius, right? So if you convert this into kelvins, so this will be 1148 Kelvin. All right. So now if you calculate T7s, this will come out to be 770.03 Kelvin. Now we have T7s and we can calculate T7. So T7 equals to T6 minus NT T6 minus T7s. All the terms we have now. So this is T6 is 1148, NT is 0.88, T6 is 1148, T7s is 770.03. So if you calculate this, T7 will come out to be 3, sorry. So this will come out to be 815. Okay, 815.39 Kelvin. Please kindly check if the calculations are correct, and if not, you can just comment in the comment box. Okay, so this is your T7. Now we have T7, T6, T4, right? T2, T1, T3. We don't have T5. So for T5, we will take help of regenerator effectiveness. This is given to us as 0.92, and we know this is this, right? This is preheating of your air, is basically the work of regenerator. So 0.72 T5 minus 381.75 values you can put this, then T5 you can calculate, maybe I can directly write the value. So I've calculated this. So this comes out to be this. Now, now we need to find out the air to fuel ratio. So how do we find out? This is question number 6 solution. So we will balance the energy, right? So through our, yes, to our heating value, right? And the temperatures we have from 5 to 6. So this will be like this. Mass of fuel into calorific value into efficiency of combustion equals to specific heat 1 plus this, okay, T6 minus T5, right? One is for air, this is for fuel. Then putting the values, we get, so in this is in kiloterms, right? Yes. In question it is given in megajoules term, but we will write it in kiloterms because the specific heat we have in kiloterms. Okay. So it is this. So now if you try to work this out, so MF will come out to be, so this is MF into 36828 equals to 456.30 plus 456.30 MF, implies MF is approximately this. Sorry. This should have been opposite, but somehow implies MF 36828 minus 456.30 equals to 456.30. So MF will come around this. Okay. Then, which means 1 by MF is 79.71, which basically is your air to fuel ratio. Okay. So this is the correct way. So air to fuel ratio is 79.71. Then estimate the cycle efficiency. So we need to find the cycle efficiency. So first of all, for the gas turbine, we have the work. Okay. So we will find for gas turbine and then for compressor, and we'll subtract from this gas turbine the compressor work. This way we'll get net work, and then the heat supplied we'll get, and from there the ratios will take of net work and the heat, and this way we'll get the efficiency. Okay. So 1148 minus 815.39. Just keep checking if everything is fine. So if you work this out, this will be this kilojoule per kg air. Then W, see this, two-stage compressor. Okay. Now if you calculate this will come out to be 149.76 kilojoule per kg air. Okay. So this is your compressor work. In that case, net work, if you want to find out, this will be gas turbine minus compressor. So if you subtract this will come out to be 213.96 kilojoule per kg air. Okay. Now heat supplied basically is efficiency has been given and this. With respect to your fuel to air ratio, right? Per kg air. So your work is in per kg air terms, so your heat supplied has to be in per kg air terms, right? Then efficiency is W net by heat supplied. Heat supplied. So 213. So this comes out to be okay. So this is your question number 7. I hope this is clear and there is no doubt. If there is, please comment it down and I will attend to it. Okay, there only. Then estimate the power delivered by the plant. Now we need to find out the power delivered by the plant. So power delivered will be in watts. Yes. So power is W net into air flow rate. Yes. So this is also there are efficiencies, mechanical efficiencies and your generator efficiencies, right? Mechanical efficiencies and one more efficiency was there. So for those, these two values have been added. So if you work this out, this will come out to be this kilowatts, or because the question asks in megawatts, so this is your question number 8. I hope this is clear. Your answer. Okay. Then it asks estimate the specific fuel consumption. Specific fuel consumption is So now first you'll find out. So this asks for specific fuel consumption in kg per kilowatt hour, right? Hour is there. So in hour terms only, first we'll find out the fuel consumption, right? Then we will divide this with your uh, work term, right? Fuel consumption per hour is equal to, so 195 we have been given. If you see, as the flow rate, yes, yes, I believe air flow rate. If you see here, this is, yes, air flow rate is 195. Okay, then for hour, so it was given in per second. So in hour we have 3600 seconds, and then because we want fuel, so when compared with air, this comes out to be this. So specific fuel consumption is 8806.92 divided by, now here is the power we have, right, which is 34929.82. Then if you calculate this, it will come out to be this. Correct? So this was about your question number 9 and the last question of lecture number 21. Then we have 3 lectures left. Before that, we'll take a short, very tiny break, and after that, we'll be back. Thank you. Okay, so let's continue with the session. We are left with very less time. Okay, so next is your Brayton cycle, where what you do is, so what is non-ideal cycle? First, it has been discussed. Then Brayton cycle has been again revised from the previous lecture, that the discussion we had in the previous lecture. Then the modifications come into picture. First is regeneration. The second is compressor intercooling. Third is turbine reheat. Fourth is water injection. So what we do in our regeneration is, we basically from the exhaust, we have gases from the exhaust of your turbine, we have combustion gases, so they are still hot, right, and they have energy, and what we can do is, so we can use this energy to preheat our air that is coming from the compressor, right. This way the energy requirement we are reducing, right, but it also, sorry, gives rise to pressure losses, right. But then if we wait the two these two changes, the uh, energy that we save in this regeneration process, right, this weighs more than the reduction in the work of the cycle, right. So this is your regeneration. Then uh, second is your compressor intercooling. So this again, the whole idea is that we want to improve our cycle's efficiency in some way. So what we do is, the inlet of your compressor, right, we try to decrease the temperature of that, right. So we do it using compressor intercooling. Okay, because eventually what will this do is, it will reduce your this will reduce your compressor work. Okay, the work that you do on compressor to compress the air or working fluid, right. Then is your turbine reheat. So what happens in your turbine reheat? So in your turbine reheat, you reheat your products, right. In in one turbine, it will expand, your combustion products will expand, then again they are reheated, and then again expansion of these products takes place to increase the exhaust velocity, right, and thus eventually you get more work from it. Then is your water injection. So water injection is done in your compressors. So this also has the cooling effect. Okay. So when the air is compressed, the heat that is generated, or the temperature that the air gains after compression. So this is in a way absorbed by this water that is used in the compressor, right? And the water absorbs it in the form of latent heat of vaporization, and this also has a cooling effect. So all these modifications are done in your, all these modifications are done in your Brayton cycle. Right? Then we have one question related to it. So please have a look at the question. Which of the following, it says that which of the following is true in a gas turbine cycle? When the thermal efficiency curve of regenerator cycle crosses the simple cycle, the effect of regeneration on efficiency is negative. Specific work increases with regeneration. So question number 10. What is the effect of regenerator? The effect is something like this. For same temperature, okay? This basically is for thermal efficiency. Like the one we had drawn earlier, okay? So NTH here, like this. So the ones I have drawn for thermal efficiency, so what happens is the so this is your simple cycle. So this is your simple cycle, and this is your with regenerator. Okay, with regenerator. With regenerator. So what happens is when this for same temperature, let's say this is what temperature T, so this is also what temperature T. So when this uh, with regenerator used, when this crosses this simple cycle where no regenerator is used, so beyond this point, if you go, it means the temperature is less, right? Is less than this, right? In that case, if you use the regenerator cycle, it is not considered effective. Okay, for the purpose which is for the purpose for which it is being used. Right? So we are trying to preheat the air from the compressor that is coming from the compressor. In that case, it has a negative effect, because basically this is the temperature difference between the your combustion products that have come from the turbine exhaust and the air that is coming from the compressor. So temperature difference between them. So if there is no temperature difference or the temperature difference is in negative, in that case there is no point of regeneration. There is no, yes, there is no chance of regeneration. Okay, so this is a true statement. Second says that specific work increases with regeneration. That is not true. Specific work decreases with regeneration, right? Because of pressure losses. Right? In that case, only one statement number one is correct. Yes, so A option is correct. This was question number 10. I hope I was able to explain this properly. Okay. Then moving on to next lecture. So next lecture is lecture number 23, combined power cycle. So what is a combined power cycle? So some cycle plus your vapor power cycle. You must have noticed that we are done with vapor power system, right? So this was done in three parts. Part 1, 2, 3, where we discussed almost everything about a vapor power system. Now we have moved on to gas turbines, right? So combined power cycle. So there is vapor power cycle first of all, and we are using some other cycle in conjunction with this vapor power cycle. Okay. So if you see combined cycle power plant, so first is your heat recovery boiler. Yes. Then is your coal gasifier. Then is your nuclear power plant. And in the last this topic, the energy and exergy analysis of the combined power cycle. So this has been done. Okay. So heat recovery boiler basically is used to recover heat from some other cycle. Okay. And then this is used to generate your superheated steam. So this other cycle can be your gas turbine, right? Then second, coal gasifier is also discussed, where we synthesize our fuel using coal gasifier. Okay, we produce synthetic fuels. Then these synthetic fuels go to your gas turbine, right? Your gas turbine as a fuel. From gas turbine, this gas turbine runs. The gas turbine has compressor, right? Then combustion, and then combustion takes place, and then your turbine that is driven from your exhaust of your turbine, gas turbine. You use this exhaust because it has heat left in it. We use this heat to some way for our application in vapor power cycle, right? So I believe in the lectures it has been said that it is used to heat the feed water, your feed water system, right? It is used in your feed water heating. So this way, coal gasifier is used, right, in your nuclear power plant. So first of all, you have a reactor in your nuclear power plant, right? And then you couple it with your vapor power cycle, right? And how do you couple it? Using your feed water heater. Using your feed water heating. This feed water heating is used in your nuclear power plants. Okay. So whatever working fluid you are using in your nuclear power plant, so this goes to your reactor, right? From there, the energy that is left in your working fluid, that is by means of heat exchanger given to your feed water heating. Right? For your coal gasifier case, the combined cycle power plant with coal gasifier. So I don't remember whether this is boiler is for steam generation. This heat is used here or for feed water heating. So out of these two, one is being used. Okay. So these are your combined power cycles. Okay. So which of the following is used as a coolant in your high temperature gas cooled nuclear reactor? So for your nuclear reactors, four options have been given: nitrogen, helium, neon, and argon. So helium is the gas that is used in your nuclear reactor, right? Gas cooled nuclear reactor. All right. So this was about your combined power cycle. And last is your gas turbine for your aircraft propulsion. So different engines have been discussed. So schematic I have already told you, right? Lecture 24 if you see. Aircraft propulsion cycle. So this basically is your Brayton cycle. Okay. So in this topic, different types of engines have been introduced. One is your turbojet, then turboprop, then turboshaft, then turbofan. Turbofan is a very important type of aircraft engine. So in your mostly most of the commercial aircrafts, if you will see, in those aircrafts turbofans are used. Okay, so all these. So turbojet basically is where by means of jet only. You are giving thrust to the aircraft. Turboprop is you will use propeller also plus jet. I hope you understand what is jet. Jet basically is the combustion products at high velocity are being ejected. So this is basically axial combustion. Okay, here will be intake, here will be compression, here will be combustion chamber, here will be turbine. Turbine is to drive your compressor. Here is your jet. Okay, with high velocity the combustion products. Also before turbine nozzle is also used. Okay, this way your combustion takes place in your aircraft propulsion system. So in propeller you have one propeller also in front. Okay, you must have seen turboprops while taking some flight, some chartered planes. They are small in size, but they have turboprops, right? They have a propeller also and then engine. So turbo shaft is used for your helicopters. Okay, so this gives your power to both your tail rotor and your main rotor. Okay, turbofan is commercial aircrafts, right? Then then thrust also has been discussed, that how you calculate thrust. So basically that is the jet thrust, right, and the pressure thrust. So at inlet there is some pressure of air and at exit there is some pressure, right? So based on that, and the momentum thrust. Okay, for the thrust expression has been given, and then propulsive efficiency expression for that also has been discussed in lecture. So I'll leave that. Then in second topic is turbojet engine. In its thermodynamic analysis, so I'll just draw this. This is what this is your diffuser. This is your compressor. Diffuser basically slow downs the air that is entering the engine. Combustion chamber. This is your turbine. This is your nozzle. So this is ideal cycle I have drawn. Okay. I hope there is no doubt in it. Okay. This is Brayton cycle only. Then is your aircraft engine. So aircraft engines broadly have been discussed here, but there is one special type of engine, that is ramjet engine. So what happens in ramjet engine? So at supersonic speeds, these ramjet engines are used. Okay, and here the compressor is not used. Okay, diffuser, combustion chamber, and then exhaust. This is there by means of nozzle. Right, so this is a special case of engines. Then there is scramjet also, that has not been discussed in the lectures. Scramjet. So what happens here is at supersonic velocities the combustion takes place. Here in ramjet engine, what we do, we try to slow down the air that is entering. Okay, and then we combust it, and then this is ejected. Right. Then rockets also have been discussed. So what is uh, important to note about rockets is that they don't have their oxidizer from the atmosphere, right? So we have air in case of these turbojet engines, turboprop, and all these engines, aircraft related engines. So the for the oxidation, we take air. But here for rockets, the oxidizer has to be carried, is carried along with your fuel, right? Because rockets have to work beyond atmosphere, right? So this is it about aircraft engines. Then quickly questions. In a turbojet engine, a combination of a propeller and exhaust jet is used to produce thrust. Not turbojet, turboprop. False statement. Which of the following engines has the highest working velocity? Ramjet. I have just mentioned you. Okay. All the others are mostly they work at subsonic speeds. Ramjet is used at supersonic speeds. So D is the correct option. After intake, a portion of airflow is bypassed in which of the following engines? So this is basically your, so if you have taken some flight from some commercial plane, right? You must have, if you have noticed, its engines. So air intake is from here, okay, from fan. Then this air basically enters. These are two lines, okay. This is casing basically. So this is casing. Here we have compressor, combustion chamber, turbine, nozzle. Okay, between these boundaries. But some air, what we do is we bypass from these sections. Okay, and this type of engine is known as turbofan. Right. So if you see the question, correct answer is D. Question number 14. This was. Question 15 says that a compressor is not used in which of the following engines? So this is your ramjet engine in which your compressor is not used. Okay. All right then. This was it about this session. So this was, I'll conclude the session. This was about gas turbines and combined power cycle. So first, we were introduced in lecture 21 to the gas turbine cycle. Then we saw questions related to it and a very lengthy numerical also based on a gas turbine cycle where intercooling was in picture, regeneration was in picture, right? So this was mix of basically both the lecture 21 and 22. So I should have put this numerical in lecture number 22. That would have been better, but I did it in lecture 21. So sorry for that. I just noticed it. All right. Then in lecture number 22, we discussed modifications like regeneration, right? Water injection and compressor intercooling, all to increase the efficiency in some way. Where regeneration was preheating of air from compressor. Intercooling was to lower the temperature of compressor to reduce the compressor work. Right, regeneration reduces the heat that we supply. Then injection also has a type of cooling effect in the compressor. So this was lecture 22. In lecture 23, we saw combined power cycles, where you combine your turbine, gas turbine system with your vapor power system, right? Then coal gasifier you use in turbine as a fuel. Then a nuclear power plant if we used as a combined power system with a vapor power cycle. We use nuclear power plant. So all these combinations can be done, right? So this was about your combined power cycle. Then is your lecture number 24, which was on aircraft propulsion systems, where different types of engines are there and their specific applications, right? And this is it about this uh, session, this week's content, and also this session. I hope this session was, in that case, informative, and I'll take leave from you guys, and we shall meet again for the next session on coming Tuesday with same timing 6 to 8 p.m. Till then, goodbye. Thank you. Thanks for watching.